introduction. Give the introduction.
So the next talk is going to be by Vasant. So he graduated this year actually, and he works on electromagnetic fields, and he has been working with Dr. Tony from SPS, and he is
also from Luciamenti.
Yes. And he is an upcoming graduate student at Skola pronounce it correctly.
I don't know how to pronounce it easily, so.
Yeah. So actually he has done a project at taking data from GMRT, which is located in Pune. So basically, so he is going to talk about his experience working at GMRT, and yeah.
Anybody knows what this is? Guess by one this one. You'll get an answer. It's not a JWST image, first.
Nebula Galaxy.
NGC6 and 46.
No. Nobody? It's an object within the Milky Way. I'll give you till the end of this talk. Alright. So, right, this talk is going to be less coordinate systems, basically no coordinate systems, and quite simple. It's going to be more like a discussion. It's going to be, just a story time kind of a talk. All right, but I promise there is a good amount of content that you will get to learn from. So something is up to this. Okay. Right. My random title, I did not know what to name this talk. So yeah. Right. The first question is like, what is it that I do? Why did I go to GMRT? What the hell was I trying to do there? And would I do that again? Stuff like this are questions even I don't know answers to, but let me try to explain what my research is and how is that related to radio telescopes and radio astronomy. Then we can take it from there and talk about some stories. Okay? So I'm going to repeat telecast a 3-minute talk I gave for some competition some year. I don't even remember when. Maybe last year, maybe a year and a half back. I don't know.
3-minute thesis.
Yeah, it was a 3-minute thesis competition. I'm going to repeat that. So first, a 3-minute detour from the content of today's talk to explain what is it that I do, and then let's get back. Okay, so this is that 3-minute presentation first. So we have a monkey, like all of you, who has a telescope, like we have in the observatory now, and the monkey looks at a galaxy, which looks like this. So, anybody can guess which galaxy this is? M1? Andromeda. Other guesses? Andromeda looks like this?
No.
Hey Vishal, Andromeda ऐसा दिखता है क्या? नहीं. Fireworks नहीं. Okay. Well, I was messing with you. This is Andromeda. Okay. How a galaxy looks depends on what wavelength you are looking at. Okay. So these are things we'll discuss sometime later, but this is a radio image. So we are looking at the radio frequencies. So I work like radio frequencies are a huge band. Like they span from somewhere around 1-ish centimeter to hundreds of meters, even thousands. So there is a huge wide range of radio wavelengths. But what I work with is actually a very thin slice in the radio, which is between 1 to somewhere around 1 centimeter to somewhere around 25-ish centimeters. Okay, this data is all like between 3 to 20. Okay, very narrow chunk if you look at the grand scheme of things. So this is how M31 looks in this narrow chunk. And now the monkey found some sunglasses. What do you guys know about sunglasses?
The polarizers.
Right? So sunglasses are they polarize the light. So it found 2 sunglasses apparently. So it is now happy. Now it is wearing these sunglasses to these observation sessions, and it looks at the galaxy, it looks different. Okay. Now the monkey has one more sunglass. It doesn't know what to do. It put one on the telescope also. Now the galaxy looks even different. Now it rotates that sunglass. Now the galaxy looks different again. Okay? So what the fuck is happening? Okay. So here is a small pattern. Top, no sunglasses, just light in radio, that is what it looks like. You put one sunglass, you get this. You put another sunglass on your telescope, you get that. You rotate that sunglass 90 degrees, you get this. So what the hell is happening? Not 90, 45 degrees and you get this. Okay. So the same galaxy, the same wavelength, it looks different just because of the presence of the sunglasses. How do you explain? What is it about the sunglasses that is, making this galaxy look different? Any guesses?
They're polarized and waves have a certain phase. If that doesn't coincide with the polarization of the sunglasses, then it blocks out the light.
Right? That is valid. That is, basically we are understanding that the polarization of the light is oriented along some fashion. Right? It has a preference in polarization. So is regular sunlight polarized?
Yes.
Yes?
Yes, that's why sunglasses work.
If you put, okay, so what does one sunglass do? If you have an unpolarized light source, if you put one sunglass, what happens? What do you observe on the other side? Yes. So it only allows that light which is polarized along the direction of the sunglass. So essentially it's a filter. So you have a huge array of possible polarizations. You are picking only those that are oriented along this side. Okay, if you have completely unpolarized, you put a polarization mask, like a sunglass. What it does is like if you have a linearly polarized sunglass in one axis only, it will allow half of the light to pass through, because half the light has that polarization, other half will have a perpendicular polarization. Everything perpendicular is blocked, same alignment is passed through. So it's like a 50% cutoff filter. Okay. So one polarization, that is what happens. If you put a second one, you have yourself a polarizer analyzer setup. Okay, you might have studied about this in your 12th. So you have both of them in the same axis, you will get some intensity out. You rotate, that intensity drops. You make them perpendicular, it drops to 0. That is what you have stated? So that is essentially what we are trying to achieve with that setup. Okay? So what we are seeing at the top is all polarizations. Whatever is the incoming light, that is just the intensity map. And this one is polarized intensity map. Okay? So if you have the sunglass, no matter if you are rotating it, you will still see that, because you do not have an analyzer here. You are not selecting a particular polarization here. But the next two, you are selecting a particular orientation of polarization. Okay? So that is the difference. And all of this is different because there is a preference. Now the question is, why is there a preference? Right? Why does the same thing look different? Why is there a preference for certain polarization? So that is what I work on. And now I am the one who, the answer lies in magnetic fields. Okay? So yeah. So now if you have this, can you see the fiber-like structures?
Yes.
Yeah. So that is my prediction. So if you have this kind of a magnetic field structure around this galaxy, then the observations you will make of this galaxy will match this. Okay, if the magnetic field were different, these observations will look different. So what I do is first do these observations, then figure out what is the magnetic field structure. Okay. Any questions?
How did you figure out the magnetic? How did you map the magnetic field?
That is my thesis document. Right? So the essential principle is, how many of you have heard of synchrotron emission? Synchrotron emission. Okay, so basically when you have a uniform magnetic field, now this is very simple case, but it gets the point across. So if you have a uniform magnetic field lines going from there to there, let us say like this, and you throw in some electrons into this video, and now what happens when you throw electrons here?
Depending on the velocity, the
Deflect.
motion will change.
Yes, perfect. So when you throw an electron, now it's going to orbit around the magnetic field lines. So depending on how fast they throw, they are going to orbit in a different radius. Now, what is happening when an electron is orbiting? It is accelerating. Right? Now, what happens when you have charges that are accelerating? Yes.
Radiation.
Radiation. So they emit light. Okay. That light is called synchrotron emission. You have these cosmic ray electrons in these galaxies. They have very high velocities, relativistic velocities, and they are orbiting this magnetic field lines, and they are emitting light. And as it turns out, you will study this if you choose physics in your 4th year. This emitted light will have a particular polarization, depending on the orientation of the magnetic field. So if the magnetic field is horizontal, the emitted light will be polarized vertically. Okay? So we are going to use that physics to figure out what is the what is the magnetic field structure going to look like. Okay? Now this one is M31. We have our result right here. Beautiful. We have our magnetic field. We are happy. But the trouble was with another galaxy I was working on, which is the Fireworks galaxy. So it's called NGC 6946. Random numbers, don't care. But what you need to know is there is this interesting galaxy called Fireworks galaxy. It is on the other side of Milky Way. Like Andromeda is away from the core, so you can look at it pretty clearly. It's huge, it is close, you can get very good data. But Fireworks galaxy is behind Milky Way's core. So you have to look through the dust and all the shit that is in the galaxy to look at this one. So, and it's more distant, it is smaller, so it's much harder to understand what is happening there. Right? So now let us get back to what was I trying to do with NGC 6946. Again, I'm trying to figure out what is the magnetic field of this galaxy, and we have some data. And by December 2023, that was like halfway into my thesis, I understood this data is not good enough. Okay, so what do we do next? So there was a winter school that was happening in Niger, where there were a bunch of cosmologists from all over India who were presenting some talks, having some discussion. They were basically hanging out for a month, not a month, a couple of weeks. 2 weeks? Yeah. So they were hanging around here for 2 weeks, and they work on something completely different, and they were thinking, okay, to make so and so discoveries, we need to go ahead and observe something. And during that discussion, me and Tuhin sir, we kind of overheard GMRT has a open observation call. That means you can propose what you want to do with the telescope, and if that is feasible, they will give you the telescope time, and you can go ahead and make those observations. Okay. So now we need to just briefly discuss why were we excited about GMRT, right? And how that fits into my work, right? Okay. So until now I have been using data from 2 telescopes called the VLA. Anybody knows the full form?
Very large area.
Exactly. Pretty dumb with naming things, yeah? Very large array.
of telescopes altogether?
Yes. So it basically has multiple telescopes, multiple radio telescopes. They all work as one telescope. Okay. So this has multiple radio telescopes looking up, and Eiffel's curve is different. It doesn't have many. It has only one dish, but the one dish is huge. It is 100 meters in size. Okay. Like literally, Usain Bolt can run across. It's that big. So we use a combination of both of this. Okay. The reason here is there are smaller dishes, about 38 meters in size, but there are 27 of them spread over a huge area. So you get a very good resolution. But because each individual dish is small, you do not you cannot catch a lot of photons. So your intensity is quite low. Okay, you will get the good resolution because the telescope size is huge, like the distances are huge, but you do not get a lot of light. So to solve the light problem, we have the other telescope, which has a huge area to collect the light. But because it's one dish, we do not get the resolution. So you combine both, you get both good resolution and enough light information. Okay, that is the idea. Now, as I said, we are dealing with 3 centimeter to 20 centimeter. Okay, this is a very narrow band, and all our data is within this range. Okay, so now think about it. So if you have electrons that are emitting, will they emit more light at 3 centimeter or at 20 centimeter? Where will the intensity be more? Think, just simple logic. 20 will be more. Reason? Okay. One reason. Others?
Larger radius, so you capture more photons in a specific area.
Basically, if you think of just distribution of energy, it is harder to accelerate these electrons to much faster speeds than to slower speeds. If the speed is slow, the wavelength will be large, the energy will be less. Right? So there will be more electrons that are less energetic than those that are more energetic. Right? Just that simple difference makes it, 20 centimeter to have more photons that are emitted at 20 centimeter. So as you go farther, it will be better. Right? But the disadvantage is VLS stops working here. Okay? So beyond 20 centimeter, we exclude. That is where GMRT comes in. GMRT starts picking up light at 21 centimeter. Specifically, 20.4, right? Which is about 1480 megahertz, something around that, and it goes down. So frequency goes down, that means the wavelength goes up, all the way to 150 megahertz, which is I think about 3 meters. Okay. Now the catch is, all the galaxies we have studied is within this range, so we do not exactly know what to expect. So asking them to observe from 20 till 3 is a bit too much. So we ask them that we will observe from 20 to 35 centimeter. Okay, to be conservative. Let's say, we know what happens here. So right next to it, it should be easy. Right next to that also should be easy. So let's do within that much. Let's worry about up to 3 meters later. That is the just to prove that we can do something with this data. We propose somewhere between 20 to 35 is what we would like to see. Okay. We basically overheard people saying that there is an open call, and we were like, let's go, let's ask them for some time. Now, then came the process of actually asking for a time. How do you ask? You cannot, ask by email. Right? I want to do this. Please give me some time with the telescope. So, what we first have to do is write a scientific justification of what science do you want to do. Right? Explain to them that we are interested in magnetic fields and we have already worked on it before, so we know how to do this job. Give us some time on this telescope and we can get it done. Okay? Write a convincing proposal. So, just because your science goals are ambitious does not mean they are practical. Okay? You then have to explain why is it that you want to use GMRT only. You are using VLA. Go ahead and use VLA. Okay. Why is it that you want to use GMRT only? Why not something like LOFAR, which works in 1 meter to I think 30 meters or 40 meter wavelength? Okay, why not use that? Okay. Why not use something like WSRT, which works in the similar wavelength range as GMRT, but it is now decommissioned, no longer working. Right? But a couple of years back it was, and it's not as sensitive, that's another issue. But why not that? Why this one? You have to justify why do you want to use this telescope? What benefit do you have? If you have no benefit, just use something else then, right? And then you have to then provide your calculations. Show them that you need this much time to achieve your goals. Convince them that this is the time requirement you have, right? So you do this, combine them into one PDF, and you submit for their panel to review. So there will be about in our call there were about 250-ish applicants, so 250-ish groups asking for time. So these observations are for a span of like 5 months. So they had 5 months of time to provide. So every week, they have some off time where they maintain the telescope and so on. But the rest of the 5 months are up for grabs. You can ask for 10 days, you can ask for 100 days. Okay, if you ask for too much, you will not get any. Right? So of course you have to justify everything. Right? So now let me just, would you like to briefly go through the proposal? Yes. Sure. First thing, the scientific justification. I'm not going to go through the text. This is what we write down. The contents are sufficient. First topic is what are we trying to do? What are we interested in? What is the science goal? Explain in that. Then, we are using a particular galaxy. Explain them why this galaxy, why not M31, which is easier to observe, right? Because it was this galaxy that is giving us a harder time, right? So, of course, we describe that. Then you explain what is it that you already have. So, we have data of this much, and we are not able to do things with it. We want more data. We ask, this is your actual proposal, what are you asking for? So we are asking to observe GMRT, at GMRT band 4, we want to observe this galaxy. And we also want to observe it at band 5 with some frequency, some band with something. Okay? And then, what do you want? Okay, you just looking at the galaxy is not sufficient. You want to quantify things. What do you want to quantify? Do you want to quantify the spectra? Do you want to quantify line emission, like hydrogen emission or something like that? So what exactly is it that you want? We want Stokes Q and U, which are basically polarization components. So, how many of you have come across Stokes parameters? Anybody? 40 people I see. Okay.
Twin Ghosh actually introduced us in
Right. So
second year.
basically, you probably will study it at some point when you do Malum's law experiment or something. Basically, it is your polarization is on a circle. Like the angle of polarization is any angle on a circle, right? So you can break it into two bases. One is like x and one is y, right? So basically, what is the intensity along x and the intensity along y will define the polarization axis. Like what is the polarization direction of your light coming? So Stokes parameters are one way to define that. That's it. It's basically one particular basis. Okay. Now, that is what we want to measure. Then there is noise. What is how many of you are attending the workshops conducted by Vishal? Few. Okay. So you might have heard him say stacking. Why do you stack? Let us see how well he has thought. Right? Why do you stack?
Because the data that we actually collect in one single instance may or may not have some errors. So we use stacking to actually fix those errors. Because let's say you have two sets of data. One of them has some sort of error in, let's say, one half of it, and the other one has some sort of error in the other half of it. You can stack the two of them and take the best portions of the both of them, and
Okay.
you get a set of data.
Yeah, basically you're minimizing that.
Minimizing, yeah.
Okay. What else? How many of you heard of this term called SNR? Signal to noise ratio. Okay. So basically, how strong is your signal compared to the noise? Noise can be thermal noise, electronic noise, whatever noise. Okay. So even in our images, when you pick good portions of single images, you are basically doing some sort of a mix and match. From 100 images, you are picking the best portions and you are adding them all up so that you get the best version of your image. So that is what you do when you are looking at planets, moon, things like this. But soon you will discuss deep sky objects where the intensity is going to be so low, the noise is going to be pretty high. So what do you do then? You cannot pick the best portion because every portion has noise now. So what you do there instead is you add all of them up. So let us say, can everyone see this side of the board? No? Fine. That's it. Okay. So let me take 1 pixel. You just have 1 pixel. Your camera is 1 pixel. Okay. So you measure. In that 1 pixel, the intensity to be some value. So this is the intensity you measure. Okay, this is the measurement. Okay. Within this measurement, you know that there is some noise. Okay. Electronic noise, thermal noise, some random photons hitting, light pollution. It could be anything. The noise will always be something below this. It will be because this is what you measure. Some part is coming from your actual source, right? And some part is going to be your noise. So your noise level is this. Okay? So SNR is basically the ratio of this to this. Okay? Now if you take one image, you have this. So with absolute certainty, you only know this much is your signal. If this is small, then whatever you're looking at is going to be very blurry, very fuzzy, buried within noise. Right? So what you do now is you add many of these on top of each other. So one image, you have this much intensity measured. If you take 2 images, add them together, this will double. So noise will also increase, but this will also increase. Okay? And noise is random. As you add more and more, it will no longer be random, it will basically be a slab. You delete that whole thing. So after you add enough of these chunks, the intensity will be sufficient that you completely put a cutoff here. Everything above this is my actual signal. That is how you isolate your signal with all of this bad trash. If you are not following, it's okay. Okay? What you are trying to do is take an image, subtract the noise out, whatever remains you keep. Do this with 100 images, and whatever you have kept will grow sufficient enough to actually see detail. Okay? You're basically hoping to see detail. So, back to this. The question is, if you take 2 images, you will improve a little. If you take 100 images, you might improve pretty good amount. If you take 10,000 images, you will improve significantly. So what is your threshold? That is the question. So if you are happy with this much amount of noise, you have to take so much amount of data to achieve that level. Right? So that is what we have defined. So we want to achieve an RMS noise of that much in band 4 and this much in band 5. Okay? So if we have this noise limits, we will be able to achieve our science goals basically. Okay, that is the hope. Again, nothing certainly. And then the question is of resolution. Okay? How well resolved your data should be. GMRT has this very unique layout. So, right. Okay. So this is how GMRT antennas are located. Okay. So you can see some sort of a Y shape. Yeah. Okay. So there are a total of 30 antennas, each 45 meter in diameter, and out of those 30, like 12 of them are in the center patch, and the rest are distributed in this Y shape. Okay. So if you use only the 12 inside here, you will get low resolution images. Because the effective diameter of the telescope is small, your resolution will be low. But if you use all of them up to the edge, you will get very good resolution. So you have to specify to them what is the resolution you are seeking. Okay? Sometimes resolution can be a bad thing, like in the previous observation. So we were zooming in too much. That means if you have very high resolution, that means the photons will be distributed to smaller and smaller areas, right? So within that small region, the amount of photons you will have will be lower, right? That means your signal to noise ratio will be worse. Okay, so that means you will need more time. So too much resolution, not great. Too little resolution, not great. So you have to find what is acceptable for your work. Okay. So 3.8 in band 4 to arc minutes in band 5. Okay, and given all of these requirements, our ask is 4 hours in band 4, 8.5 hours in band 5. Okay, so you can there are tools to calculate, and you can do that. So this is our previous data of VLM and telescope at 3 cm and 6 cm, just to show that we are not lying, right? And then we talk about what do we intend to do next. Okay, now after these observations, what next? Okay, I will come to this part a little later, and then then we went on to mention, has any of this kind of observations been made on GMRT before? Has your team or the operators there, have they done this kind of work before? The straight answer is no. Okay, we are the first team to do polarization observations of a galaxy. People have tried it with pulsars in band 4 and have recently succeeded. Okay, so nobody has done it on an extended object, and pulsars are very bright. If you don't know that already, pulsars are freaking bright compared to galaxies. Okay, because they are very sharp point sources that are very high. So people have made simpler observations of just measuring intensity. People have measured hydrogen emission, not of this galaxy but of other galaxies, but nothing directly on polarization yet. So our basic proposal was, okay, we need this data at this wavelength, which your telescope can do. You don't know if your telescope can do it, so we will try it out and check. If it can, others will also use your telescope, which will be good for you. Right? So you have to convince them that if you are able to do a successful measurement, then there is a future for these kind of measurements in terms of other galaxies or other observations, especially for polarization. Right? And then you go on to justify, in short, why is it that you want to use GMRT, not any other telescope. A little more about why those frequencies and why that noise level, why that resolution, all of those random numbers that I just mentioned, you have to explain. Once you are done, they have a pretty good simple calculator where you give all of your requirements, and it provides you what is the time that you need. Total time that you will need is that much. And then it will give you what other issues you might face for your reference. So you do that for both. And our total ask was somewhere around 14 hours of total observation. That means 2 nights on the telescope. to measure the polarization emission from NGC694. Okay. Once you do this, they go into a bunch of table conferences. They discuss, they evaluate everybody's proposal, then they rank. What is the most interesting science case they received, and what is the worst? They stack them all up, and if you are like, then they allot the time. So sometimes you ask for 45 hours, and we think 45 hours is too much, so 35 hours, that's it. We have. Okay, that kind of cuts happen. We got full time, luckily. So, once, like I think this year there were about 80 or 90 scheduled observations out of 200 proposals. So it's quite competitive. Then you will be informed if your proposal has gone through. Okay. You have received time. So when would you like to observe? What are your preferred dates? Any reason you cannot come for some months or whatever. So you explain to them, okay, sometime here because of some reasons again, and that is the scheduling part. So they will, you discuss with the observation committee there and decide when you're going to make these observations. So we decided on last week of July, after my convocation and all that is over, so that I will have enough time to go there, do the observations and come back. And once they have scheduled your observations, you have to prepare something called the command file. Just like our telescope, we operate with the computer and everything. These 30 antennas are also all operated by telescopes. Okay? So you have to tell the telescope where to look at, what to look at, what data to record, what data to throw away, right? So you do all of that. So you write a file which says, okay, go to this source for this much time, then go here for this much time, do blah blah blah, and then wait here, then blah 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 blah. So you give a list of commands that the telescope will follow. And the final step is just go there and get the job done. Okay? That is how the entire sequence of events happen. Right? So now, any questions until here? No? This was just story boring. So now is the
What
interesting
if it rains at that time?
Why did you ask for different resolutions in two different
that is because with wavelength, your resolution of the telescope changes. How many of you remember the equation for resolution? It involves aperture, right? The diameter of the telescope. But it also involves what frequency you are dealing with. So recently, again, we were looking at Jupiter. And if you look at Jupiter, an image in using our sensor itself, in blue, you can see the image is sharper than in red. Okay? It is not the telescope's problem, it is just wavelength being longer. Longer the wavelength, harder it is to achieve higher resolution. Okay? Shorter wavelengths are better for higher resolution. Okay? So that is why we have different resolutions quoted for different wavelengths. Ideally, we are using all 30 antennas with the highest possible resolution mode, and that is what it can do.
How did it came up with these size numbers?
Oh, that is okay. So okay. The way arrays work is your resolution is dependent on something called the longest baseline. So baseline is the distance between two antennas. Okay. So if you have any two antennas, the distance between them is the baseline. So the longest baseline defines your maximum possible resolution. Okay. So you have to imagine what the hell is happening during the observation to picture how your telescope is working, especially in terms of these interferometers, right? I didn't intend on covering this, but now that there is a question, I will. So, your antennas are fixed on Earth in a Y shape, right? Let it just be like, I will just draw it as a Y. Okay. Now, over time, the object is traveling in the sky, and your telescope is not in it's in an all azimuth mode, right? So object is going to rotate in the field of view. So if you keep the object fixed, it is equivalent to having your telescope rotate. Following? That basically means your arms are moving with time like this. Okay? So, if you were to have enough time to take this arm from here till here, that is the object covers enough time in the sky, that is equivalent to this arm covering enough arc length here, you have essentially made a telescope that is this big. Understood? Okay. So now, when you do not have a full Y like this, what you have is individual points, small antennas on this, right? So what they end up tracing is like an arc, like this, something like that. So you basically have an incomplete telescope. So you do not have a full dish. You have basically chunks of the dish distributed. Okay. So what? So if your chunks are just this much, something like this, this is your maximum distance between the antennae. So effectively, you are a part of a telescope that is like this big. So that defines your resolution. Okay? Like I defined, the distance between these two antennas is called its baseline. The longest baseline defines your resolution. Okay? So, if you have something very small pieces like this, okay, if you have too small of pieces, these are not there at all, essentially you now are dealing with a telescope that is effectively of this diameter, but because there are such short lengths, arcs spread across, your resolution will not be very reliable. So it is going to be something lesser than that. So, okay. So you need to have enough length coverage, and you also need to have them spaced distant enough to be able to get good resolution, good diameter. Okay. So that is how these arrays work. Because you do not have this entire size telescope, you're basically constructing the telescope from bits and pieces. Okay? Now the next principle is how do you make a radio observation. Before that, how do you make an optical observation with our telescopes that you have? Vishal, did you discuss calibration before? No? Okay. Fine. So basically when you look at an object, what you see on your camera is a RGB value. So if you have a mono, let's simplify, you are like us, hardcore using monochrome cameras, then you basically get a number that corresponds to the pixel value, the pixel intensity. So for our cameras it is between 2 power 0 to 2 power 10. It's a 10-bit camera, so it goes up to a maximum of 2 power 10 value. You basically get a number out, somewhere from 1 to 2 power 10. Right? That number is not the intensity itself. It is a representation of intensity in this digital space. Right? So if the intensity is 1 watt per meter per 1 watt per meter square at a particular wavelength. So per nanometer intensity. So if that number is small, this number will be small. If that number is high, this number will be high. They need not be linearly related, because there is a bunch of electronics that goes between your photon hitting the sensor to the electron readout that you get, the digital readout that you get. So what you actually have to do is you need to pick a star or another object whose intensity you know, or whose intensity you have defined to be something, and you measure everything else related to that. Okay? So what you are basically doing is, this is my reference. This gives me a intensity value of say 100. I will go to some other star. It gives me a value of 1000. That means if assuming a linear relation, that one which is giving me 1000 is 10 times better than the one which is giving me 100. All of of your intensity measurements that you make are relative. To make absolute, you have more complicated things to deal with, but you can do that also. Okay? So basically, you need some other sources that you know beforehand to use as your references. So those are called your calibrators. Okay? So we use Vega as magnitude 0 calibrator. That is the standard in astronomy, mostly for visible. But these are all wavelength dependent. Okay. So when it comes to optical light, the phase of the light does not matter to you. Okay? Everybody knows what phase is. Clear? How much time do you have? 2 hours? Okay. So in optics, like visible light phase does not matter much. So all you care about is the total intensity. But in radio, because the wavelengths are so long, like they are 20 centimeters in size, they're physically this big waves, right? So if a wave that is this size is off by 1 or 2 centimeters, your detector will be able to make that difference out. It will measure that difference. Okay? So you also have to calibrate the phase. Okay? So flux calibration is the intensity calibration. Phase calibration is calibrating for that difference in the wavelength phase. And then we are interested in polarization observation. So you need to again pick out an object which is polarized in one orientation that you already know to be used as the reference. So use the polarization calculation. So basically this is how observation loop will run. So you look at all of these calibrators. Okay, you determine what is the flux on the phase and the polarization of known sources. Then you go to your target, you observe your data. But these things do not remain constant overnight. They change very fast. They change within like an hour. The atmosphere is changing, the higher atmosphere, and also the relative location is changing. And the electronics that is on your system, that is changing, its temperature is changing, the antenna's temperature is changing. So everything is changing. So what you basically have to do is every half an hour, you need to loop this observation cycle. You go to your target, you look at it, then you go to your calibration, all the calibrators, you look at them, then you come back to your target, then you go back to all the calibrators, you look at them, you come back to your target. Okay? So essentially, if you need 20 minutes of time on your target, you have to do a total looping of like around 40 minutes to go to these other calibrators and observe them properly and come back to the target. Okay? So we had overlooked the time it takes to go from one calibrator to the other. So we ended up losing some time at the end of the observations. But overall, this is the procedure. Okay? So now you know how radio observations work. The next thing is, this is the last slide I think. Now you have the data. You have the data of the calibrator, like flux calibrator, phase calibrator, polarization calibrator, and your source. So you take these 4 items together. Then you are like, okay, given the flux of my reference, my target has this flux. Given the phase of my reference, my target has to be phase adjusted this way. Given the polarization of source, like the known source, the target has a polarization of this much, of this angle. So you use these 3 to determine the target. That is one data set kept aside. Now you do that with the next set of calibrations. And then you do that with all of them. And then you have the final set of a bunch of your source images, which are calibrated images, like the calibrated data. You take that, you add them all together, you stack essentially, and you get your final plots. That is, the Stokes parameter, the polarization angle, and the polarization intensity, things like that. Now you are ready. So basically, after doing all of this, you have built those 4 images that I first talked about. Okay, and then you then use those images to study your magnetic field. Okay, that's it.